So we've talked a lot about the structure of the atmosphere and its basic physical properties and how energy flows through the system and the role that water vapor plays. You can think of all these things as being the basic building blocks of weather, but even more so, you can think of it as being the basic physics behind climate. So when we get back to the climate problem at the end of the course, we'll refer to a lot of the stuff that we've done already. But today is the day we say enough with the energy, enough with the humidity. I want to know about winds. To which I say, patience, grasshopper. But that is where we're headed. So we're going to start talking about circulations and winds today. So what is the wind? So let's suppose you go outside and you've got a wind blowing from the west. So let's suppose you're facing the west and you feel the air hitting you on your face and going past you. Well, what that is from the atmospheric scientist's perspective is that really is just air moving from one place to another. In this case, it would be air that was over in the west, and that air is moving towards the east. And as that air goes past you, you feel it as wind. And of course, the reason that the air is moving around from place to place the way it does is because of the forces that act on it. Basically, the air goes where the forces tell it to go. And so the first starting point then in thinking about winds and circulation is really to think about the forces involved, the forces that are driving the air to go from one place to another. And probably the most important of those forces is our pressure force. So we're going to start off this screencast by going back and reviewing some basic things that we know about pressure and extending them a little bit. Now, you'll recall that there's two different ways of thinking about pressure in the atmosphere. At sort of the most basic level, pressure is just this tendency of an air mass to push outward on its surroundings. That is what air masses do. It's just one of the things that they do. That's why the balloon stays inflated when you blow it up, because the air is pushing outwards on the balloon. Now, in the context of the atmosphere, typically the surroundings are other air masses. So if you have an air mass pushing outwards, it's pushing outwards on other air around it. And that air around it is also pushing outwards. And so it ends up pushing back on the original air mass. And so in that sense, the air mass ends up staying confined. It doesn't just expand outwards. It ends up being confined because the other air masses around it are pushing on it and prohibiting it from expanding outwards. So from a conceptual standpoint, then, you can think of the atmosphere as being divided into a bunch of little air masses, and all of those air masses are pushing on each other through the action of pressure. We're going to come back to that basic idea later when we're thinking about how pressure drives the winds, but for the moment I'm going to put that aside and go back to the second way of thinking about pressure. Now, the second way of thinking about pressure in the atmosphere was that at any given level, the pressure is related to the weight of the air above you. This is something that we described quite a bit earlier, but I'm actually going to make a note of it again because this is an important concept. It plays an important role in understanding a lot of different things about circulation. So let's just note this again. So at any given height in the atmosphere, the pressure equals the weight of the air above that height. At any given height in the atmosphere, the pressure is determined by the weight of the air above that height. Again, the idea was that if you're at some level here in the atmosphere, you've got a bunch of air above you. There's a big old mass of air up here, and in order to keep that air up, something has to hold it up there so it doesn't fall. And the thing that holds it up there is the pressure force from the air below, pushing upwards. And so the pressure force at that height is just going to be equal to the weight of the air of the column above that height, because you need exactly that much force to hold that air up. I should note, actually, maybe I'll sort of digress here for a second and speak frankly. So I noticed that there's a number of engineers in the course, and if you guys have had a course on fluid dynamics, you might realize that this idea isn't exactly right. The pressure isn't 100% determined by the weight. There are other factors involved here. But for the purposes of the atmosphere and the kinds of circulations we're going to be talking about, it's a pretty good approximation. And it's a good enough approximation that we're just going to take it to be true. At any given height in the atmosphere, the pressure is determined by the weight of the air above that height, to a very good approximation. Okay, that being the case, if we remember that weight is just proportional to mass, it's the mass times the gravitational constant, then we can also say that at any given height in the atmosphere, up here, the pressure at that height is determined by the amount of mass above you. More mass above you gives you bigger pressure. Less mass above you gives you smaller pressure. Okay. And of course, this allowed us to infer how pressure varies with height, because if you go upwards through the atmosphere to a higher level, now there's less mass in the atmosphere above you. And because there's less mass above you at this point, the pressure up here is less, because the pressure is determined by the mass above you. So pressure decreases with height. Pressure decreases with height. Okay, so those are all pretty basic concepts and things that we looked at before. And of course, by extension, if we go downwards through the atmosphere, the opposite happens. If we go downwards, now we've got a lot more mass above us weighing down, and because we have more mass up here, that means the pressure down here is going to be bigger, because the pressure is determined by the mass above you. All right, so that's all stuff that we did before. Now let's extend this just a little bit. Let's introduce a couple of corollaries. So I'm switching into math speak here. Corollaries. A corollary is basically just something that follows directly from things that we've already stated to be true. So if we know all this stuff about how pressure is related to the weight of the air column, then what can we infer from that? Well, the first thing we can infer, the first corollary, is that since the pressure is determined by the mass above you, then if you go to any given pressure level in the atmosphere, say 500 millibars, and you go back there and you go to that level at different times a day or different seasons or whatever, it doesn't matter. Since the pressure is determined by the mass of the air above you, if you're at 500 millibars, you always have the same amount of mass above you. It's the amount of mass that gives you 500 millibars worth of pressure. Another way you can say the same thing, actually, is that millibars, being a measure of pressure, is really also a measure of weight, right? Pressure was determined by the weight per unit area. So millibars is really weight per unit area. We can ignore the per unit area part for the moment and just think of it as being a measure of weight. And so if you're at 500 millibars, what it's telling you is that the mass of the air above you weighs 500 millibars. That's exactly what it's saying. So in terms of the sketch over here then, if we're at 500 millibars, then the part of the column above 500 millibars, that level, the 500 millibar level, that part up there, so its weight of this part of the column is always going to be 500 millibars. Regardless of when you take that measurement, if you go to that level, 500 millibars, it's telling you there's 500 millibars worth of weight above you. 500 millibars worth of mass above you, if you like. And it doesn't matter the time of day, it doesn't matter the season, it doesn't matter if it's Amazon Prime Day or your precious Betta's birthday, it doesn't matter. If you go to the 500 millibar pressure level, it's telling you there's 500 millibars worth of weight above you. So regardless of location, time, season, temperature, whatever. Okie dokie. So there's always 500 millibars worth of mass above you at that level. Now let's suppose we consider two pressure levels. So let's draw in our little column here. There's our little column. extending from the ground upwards. Maybe we'll shade in the ground so we know where the ground is. And let's suppose we think about two pressure levels. So we'll put one pressure level here. Maybe I'll let you guys catch up on the sketching for a second while I admire how pretty my column is. Nice square edges. And let's say I have a second pressure level up here. And it doesn't really matter what the numbers are on this, but to be concrete, let's give these guys values. Let's say that the bottom pressure level is 500 millibars, and let's say that the top pressure level here is 200 millibars. So we've got our two pressure levels. Now, from what we just went through before, we know that if we're at 500 millibars here, let's look at the bottom pressure level first. What that's telling us is that the weight of the air column above you, oh, it looks like I'm doing 200 first. I forgot the order of my sketches there. So I think I may have mentioned this in one of the previous screencasts, but I actually sketch all this out beforehand and then play it back while I'm recording it, and I forgot which level I'm doing first. But we're going to do the 200 millibar level first. So let's think about the 200 millibar level. Based on the explanation that we just gave on the previous slide, if we're at 200 millibars, if that's our pressure, that's telling us directly that the weight of the air above us is 200 millibars worth of weight. So we've got 200 millibars worth of weight in this part of the column here. On the other hand, if we're down here at 500, that's telling us that the column above there weighs 500. So that part of the column weighs 500. So by direct extension, that means that the part in between has to weigh the difference, because the part up here weighs 200, the whole thing weighs 500, which means the part in between has to weigh 300 millibars. And again, it doesn't matter the time of day, the season, and so forth and so on. If we pick these two pressure levels, 500 and 200, the amount of mass between them is always 300 millibars worth of mass. It's always the same amount of mass between those two pressure levels. Maybe it can be useful to think about this again in terms of our analogy with a stack of books. So if you've got a bunch of books, let's say we have 10 books, and each of the books represents 100 millibars. Well, if you put your hand in here below the top two books, you feel 2 books worth of weight. And then you put your other hand in down here below 5 of the books, so halfway through the column. And now the weight that you feel above that hand is 5 books. So clearly then, the weight in between has to be the difference. You had 2 above your top hand and 5 above your bottom hand. And so the part in between your two hands has to be 3. Has to be the difference, 3 books in between. And it's always going to be that same amount of weight regardless of the situation. So if we go back to our previous figure on the previous slide, then what that's saying is that if we just think about if we have the 200 millibar level and the 500 millibar level, the part in between has to be the difference between them. It has to be 300 millibars. So this part weighs 300 millibars. So that's corollary number 2. And of course, it doesn't have to be 500 and 200. This works for any 2 specific pressure levels. Once we know the 2 pressure values, that tells us how much weight is in between those 2 levels. And it's always the same amount of mass in between those 2 levels to produce that certain amount of weight. So the corollary then looks like this. Given 2 specific pressure levels, the mass of air in between those 2 pressure levels is always the same. It's the amount of mass that produces the difference in pressure. Okay, those 2 ideas are going to be useful as we move forward. Now let's think a little bit about pressure at the ground, which we usually refer to as surface pressure, pressure at the surface of the earth. And I'll be a little bit more careful about this later. As we'll see, it's not exactly the ground we're talking about here when we look at surface pressure typically. But for the moment, we'll just say that it's the ground because that's it's the right basic idea. So now pressure measures the weight of the air column above you. So if we're thinking about the pressure at the ground, down here at the bottom of our air column, that's going to be determined by the weight of the whole air column above you. You can actually think of that pressure reading as being a measure of the weight of the air column. Whatever that air column weighs, that's what your pressure is going to be down here at the bottom. So what that means is that the only way we can change that pressure is to change how much the air column weighs. i.e., the only way to change the surface pressure i.e. the pressure at the ground, is to change the amount of mass in the air column. The only way we can change the pressure at the ground is to change the amount of mass in the air column. So if you guys have a home weather station and that home weather station records pressure, you'll know that the pressure goes up and down. Some days it's a little bit higher, some days it's a little bit lower. And what that's telling you is that some days the air column above you weighs a little bit more, and some days the air column above you weighs a little bit less. That's what's going on there. So if you're going to change the pressure, the only way you can do it is to take mass in or out of the column. So how are we going to do this? Well, one way we can do it is have air that converges into the column. Converging here basically just means air that's coming together. And so if you have air that's coming together into your column at some level, I'm actually drawing diverging here, but if you had air that was coming together into your column, that would be bringing mass into the column. It would increase the amount of mass in your column, and so the pressure at the ground would go up because it's determined by the amount of mass. Conversely, if you have air diverging like I've drawn, so here I've got air that's diverging, it's going apart, and that's going to end up taking some of the air that's in the column and moving it out of the column. So you end up having less mass in your column. You took some mass away, so you have less mass in your column. And because you have less mass in your column, the pressure down at the ground goes down because you have less mass. So that's really the only way that we can change pressure at the ground, is by bringing mass into the column through convergence or taking mass out of the column through divergence. Specifically, divergence, as I've drawn here, takes mass out of the air column, decreases the surface pressure. Divergence from the column tends to decrease surface pressure. If instead you have air coming into the column, that's convergence, that increases the surface pressure by increasing the amount of mass in your column. It's actually seems kind of magical that this is the way it works, but it is the way it works. If you have divergence up here above you, somewhere in the air column, the pressure at the ground will adjust very quickly to be less because the weight of the column is less, and so the pressure at the ground will go down just by taking the mass above you away. But we have to be a little bit careful when we apply this idea to thinking about pressure, because it typically turns out that if you have divergence from your air column at one level, then you're going to end up having convergence at another level. As I've drawn it in here, I have divergence above, and that ends up giving me convergence down here. So let's think about that for a minute. Why would that be? Why, if you have, say, divergence at one level, do you have convergence at another level, or vice versa? So maybe let's sketch that out. Okay, so let's maybe sketch in our column here, thinking about the weight of this column. Maybe I'll draw in the ground down at the bottom again. You might notice how much this column looks like the previous column that we had earlier in the screencast. That is skill, all skill, particularly copying and pasting skill. So we've got this column here. Let's say we've got some convergence aloft. So up high in the air column, we've got air coming together. So what's that going to end up doing? Well, that brings mass into the air column. It increases the weight of the air column. And so as a result, the pressure at the ground goes up. Now, we haven't talked a lot about this yet. We're going to get to it, but it should be relatively intuitive that if you have a region where pressure is relatively high, then that's going to tend to push the air outwards into the surrounding regions. And so as a result, by pushing the air out away from the high pressure into the surrounding regions, we end up driving a little bit of divergence. So the end result then of that little causality chain is that convergence up aloft ended up driving a little bit of divergence down below by way of the interaction through the pressure. So this then is the basic mechanism of how convergence at one level will be related to divergence at another level, and vice versa. So when we're thinking about pressure at the ground and the weight of the air column, we really have to be thinking about the weight of the whole column, which means we have to think about divergence and convergence throughout the whole column. It's really going to be the net divergence or net convergence that determines the weight and hence the pressure. And when we have convergence or divergence at one level, we usually typically have the opposite at the other level. So you have to be careful in adding them all up. Now that said, I will say that most of the time, I have this noted down here, sort of as a rule of the thumb. This pointer is really kind of tricky to use. I'm all over the place with the pointer. So most of the time, as a rule of thumb, this isn't 100%, but most of the time, what's going on at upper levels is going to dominate. So the upper level process is going to win. So in other words, for instance, as the case I have it shown here, at upper levels there's divergence, which takes mass away. Down below we have convergence, which brings mass in. As a rule of thumb, most of the time, the upper level process is dominating. So the net result will be you'll lose mass. And you can sort of get a sense of that from the way I drew the arrows. I drew the arrows as being bigger up above and smaller down here to indicate that the divergence aloft is the dominant process. And so that's actually going to determine the change in the surface pressure. Okay, so let's take a break here and split this up a little bit. And then when we come back for the next screencast, we'll talk about surface pressure maps. That is how we draw out maps of pressure at the ground.